hello everyone. My name is Alicia Lozano-Diez, and I am from Universidad Autónoma de Madrid, from Spain, and I will be working with Ramani and Santosh and the rest of the team on large audio language models. So with the big help of Fernando and the rest of the students, Sara and Laura and Lasha will also present a little bit later. We have prepared a notebook that I think Fernando has already shared with you. So everyone can run the things, and I will go step by step through the notebook. Still, I have it already run, so you can see the outputs here, and we can see what we are supposed to get. We have made a big effort to make it work in Google Colab. So that's why we took the smallest models and so on. And sometimes there are some tricks that we had to do, like to run a couple of times something to fit into memory and things like that. But I will let you know where those tricks are, because sometimes it runs the first time and then sometimes it doesn't. So I will let you know and apologize in advance because we didn't manage to make it like properly run. But I hope it's still interesting and we can get something out of it. Of course, anyone can interrupt and ask questions anytime. I'll try to answer. And of course, there are some other experts in our team that could also help with details and so on. So, as I said, basically what we are going to do is explore these large audio language models. And in particular, we took for this notebook the Audio Flamingo 2 that already Ramani mentioned before, and the MMAU data set, and for that we only have some basic setup and statistics and so on. So we gave you, it's very clicky.
Is it work? Yeah.
Is it every time I scroll or it's random? I don't know. Yeah, okay, I can manage.
I can bring another one.
And you have it in your screens, hopefully. Does everyone have the notebook already? Yeah? Okay, so you can run it. There are some things that will take a few minutes. We managed to get it like up to 5 minutes, some things. But let me know if you're stuck and we can stop and I can help.
Just if I say something, you might ask for GPU environment first and then you can run all the cells.
Yeah, for me it gets disconnected at some point and then I basically ran out of time of GPU while I wasn't using it because there are some things that didn't use GPU, but if you run it all at once, then it's probably okay. But the only issue is the environment. I will let you know with the requirements now in a bit. So basically, we gave you here the reference of the 3 papers that are mainly involved in this notebook. Once I finish, we will give the floor to one of Ramani's students. He will connect and give a very short presentation on question and answer pairs. And finally, Lasha will show you a small example of how to maybe do some fine-tuning or training of these models, because this notebook only covers inference. We didn't run any fine-tuning on Google Colab due to computational resources, basically restrictions, at least on the free version. So first of all, the notebook outline is setting up the Python environment, and I will give you the trick to make it run with all the versions. Then explore some of the CLAP, which is the model that is used within Audio Flamingo with some modifications, but it's basically the audio and text encoder and we will explore some examples of the embeddings that are output from this model. Then how to use Audio Flamingo 2 for inference on different audios. And some of the stats regarding the data set that this has been tested on mainly, and then inference on some questions that you may come up with to test and infer on the model. As I said, we have used a reduced version of the Audio Flamingo 2 that is mainly on the paper. It's 3 billion parameters, while here we use the 0.5 due to, again, Google Colab restrictions. So the GitHub is all here. Thanks, Fernando, for setting that up. And first of all, you clone the GitHub, and then you install the requirements. These are, some of them are probably not needed in Google Colab, and that's why we didn't manage to remove and get only the ones that we needed. But basically, after a while, you will get this error, but after that, everything runs. It says restart the session, and then if you restart it, then all the requirements are already set for the rest of the notebook. And sorry about that, but we didn't manage to solve that. So, of course, as I said, if anyone has any issues, just stop me and we can have a look, any of us. Okay, so this is only setting up the requirements, and here's where the notebook actually starts. So what is the first part? The CLAP model, which is this contrastive language audio pre-training. It's a model that was published previously to Audio Flamingo 2. And what it does is to have basically related also to what Santosh was presenting before. It has an audio encoder and text encoder, and it tries to basically get those embeddings, learn embeddings that are close to each other if the audio and the text is related. So it is trained with contrastive learning, similar to the other model based on image. So the audio encoder, in the paper, they use two different audio encoders. One is based on CNNs, and the other is based on transformers. It starts from spectrograms or MEL filter banks, and basically it produces embedding vectors. In the paper, they have some tricks to do variable length and so on, but basically these are the main ideas. And it's, of course, trained to capture the information, the semantic content out of the audio. So in this part, in this audio encoder, it's only based on audio. So what is the other part doing? There is also a text encoder. I will show you the image, maybe. So this image is from the paper. So they have the audio, and they do things when the audio clip is shorter than 10 seconds or larger. They just basically chunk it and use those parts and combine the features. That's a trick specific from the paper. And the text part is a transformer-based encoder, text encoder, and they compare different encoders, such as Clip, Bert, or Roberta. And again, the main aim is to basically have the sentences and get some embeddings out of them to combine them with the audio embeddings. So out of the audio and out of the text, basically what we get, it's embeddings. And these embeddings are paired by this index. These are the embeddings with the A, are the audio embeddings, and these are the text embeddings. So what we want is to have high similarity in the pairs in which the audio and the text basically comes from the same idea, or they are similar in the sense that the text is explaining somehow the audio. So how is this basically used afterwards? So in the paper, they show different applications. Two of them are zero-shot audio classification, in which they use the embeddings, the audio embeddings, and given some classes, they basically prepare a very simple prompt, such as this is the sound of a dog, for any of the classes. So you get the text embeddings, and basically what you are trying to do is to check whether this audio embedding is closer to any of these embeddings that come from a very simple prompt text that is defined in the class. So that is one of the applications, and then they, of course, they can use also some supervised audio classification, and but we will see some examples of the embeddings and how they match in this basically setup of zero-shot audio classification. So here is the code. First, we, of course, import the libraries that we need for this club, which I must say that is not exactly the audio encoder. I will mention this later as well. But it's not, I lost the, it's not the same audio encoder and text encoder that is used in Audio Flamingo, because in Audio Flamingo, it's a modified version of this, but it's the same idea, basically. It was just trained and improved out of this one. So what we wanted you to explore in this first part is this embedding, how the model is basically representing the information regarding different audios. So this is just loading the libraries that we are going to use and the checkpoint for the club module. And if you manage to run up to here, is everyone okay? And restarted the session after the requirements, okay? So then, as I said, we can use it for zero-shot classification as seen in the previous picture. And you have different audios to test the system on. They are all in the directory assets from the repository. And you have some audios that, for example, from a cat, from a dog, from someone coughing. And then you can make questions or descriptions out of them, and then see how the embeddings for the text and the audio are similar or not. So here you have, well, this is because of the restart, the trick that is solving that. And once you, for example, I have selected here the cat and the dog audios, just so you see how it sounds. And then the second one. Oh, it changed to my... Okay, so these are the two audios, and what we are trying to see is whether the embeddings out of, from this model out of this audio are similar or not in terms of distance. So with this piece of code, what you can do is to extract the embeddings from the audio encoder from CLAP and compute some distance out of them. So these are the embeddings that are output from the model, and basically you can do the same with some text. Imagine the test is something as simple as this is a sound of a dog, this is a sound of a cat. This is the example that I mentioned that they used in the paper for classification. So basically they prepare this small prompt that is related to the classes. Imagine we want to classify those audios regarding or related to the classes that are dog and cat. And then what we can do is to have the embedding from the test, the embedding from the audio, and compute the distance. So this is what is done here. We get the audio embeddings and the text embeddings, and we can compute the similarity between those pairs. We have two audios and two prompts. So we have distances, well, in this case, similarity between the embeddings that are basically the same class, let's say, the audio from the dog and the text, that this is the sound of a dog, and the second one with the cat. So we get the largest similarity related to the pairs that are actually same idea, same content. And then what we have here is pretty much the same. So we are going to represent using a projection to 2D dimensional, because the embeddings, I think they are 512 dimensional embeddings. And here we represent these four embeddings, the embedding audio cat, the audio from the dog, the text dog, and the text cat. And what we do is to basically represent these embeddings and see how they are close to each other or not. So this is just the UMAP projection. And what we see is the text dog embedding is here, the audio dog is there, and the text cat is here, and the audio cat is there. So, of course, in this case, the text has some parts in common, so that's my guess of how text embeddings are closer, in the sense that both of them say this is the sound of, and then cat and dog. The only difference is the cat and dog, but still it's able to separate them and make them closer to their correct, basically, class in terms of audio embedding. Again, we can compute some similarity or distance. Thank you. And for some other, for example, for some other audios, here we have the dog and the cosine similarity between the text that instead of saying this is the sound of a dog, it says this is a dog barking. But still, it's describing somehow the audio. So we expect a distance that is, let's say, small. If we use some other audio, in this case it's a longer one, and it's pretty clear what it is. Okay, so if we have that audio now, and we pair it, or we compute the distance with the text, this is a dog barking, then of course we get a much larger distance in terms of cosine than with the dog audio, which is, of course, the idea. Up to here, everyone has been able to run it? Okay. So this is basically the idea behind, or what it is used to encode the information that is input to Audio Flamingo 2, which is the model that, as I said, Ramani mentioned before. And well, he showed samples as well for Audio Flamingo 3, which includes speech. In this case, it wasn't included in this version of the Audio Flamingo 2, but we use this one. And what is this model about? So the model basically has is advanced audio understanding and reasoning, and we will see again some more pairs of audio and questions that it's able to solve, and it's similar to what Ramani has presented before. So, for example, there are 3 different tasks here that it's able to perform. One of them is audio captioning. For example, describe what you hear. The second one is sound event detection. For example, it's able to answer questions like, is there a siren or siren in this audio? And question answering with audio, like which is the mood of the second speaker. So it needs to reason to answer these questions, and this is the main aim of the model. So what's the architecture here? So what we have is basically an audio encoder. Is this based on the previous audio encoder, CLAP? It only adds some improved version, basically, in which they train with more data and more curated data set. And, well, basically they include some sliding window and things like that to make this encoder better than CLAP and to basically overcome some limitations. And what it does is we have the audio. In this case, it was an audio that it's music and a hammer beating. And this encoder, audio encoder, gives us a representation of the audio in terms of embeddings. Then what we have is a transformation layer. This is similar to the idea of what Santosh was presenting before. So we need to somehow align the embeddings coming from the audio to the language model that we are going to use for decoding. So these transformation layers are some basically, I think it's only a projection, I believe, MLP. But I need to check, or self-attention, I think. And then we have this gated cross-attention in order to take into account the information of the audio and the information of the text. Here we have the prompt, is basically the question, we receive this audio, and the question is, what is unusual about this audio? With this, we use a tokenizer. It's a language model. And basically what it does is to find similarities between these embeddings and the question to respond. And the answer is the unusual aspect of the audio is a combination of the music and the sound of mechanisms. So this is what the model is able to do. As I said, what we use, well, here in the paper, the model that the authors test is the 3 billion version, both for the decoder-only model, which is QN 2.5, 3 billion, but what we have here is the 0.5 billion, okay? So, of course, you won't get as good results as with the larger one. Then the rest is the same, and the language model as well is the reduced versions. So what do we need? Basically to download the models, we can use this script. Of course, these scripts and everything is set up in the repository, so you can have a look at the script and how it is performed. But in this case, it's only downloading the Hugging Face model, Q1 2.5, and the Audio Flamingo 2 that it's compatible with this 0.5 billion parameter encoder. You need to replace there your Hugging Face token, and after a while, you can download it. Is that correct? Everyone managed to download it? Yeah? Okay. So we end up with our models here, the checkpoints. Of course, this is all inference only. So we are not training anything, and we are only running inference. If we see, once we have these two models downloaded, we can use some audio file. For example, in this case, is this dance Matisse music audio, also from the assets part. And you have here the config file, the inference file, which is also here. You can see the parameters, but mainly what it sets is the parameters to load the pre-trained model and then do the inference on it. You can test, then you will have some time to basically test different things. In this case, what we do is to give this audio that I don't think I have loaded here, but you can listen to it. And the prompt or the question is caption the audio. And with this code, with this line, basically we can run the inference. And here's the second trick that we didn't manage to. Well, sometimes it runs at the first time, sometimes it does at the second time. It depends on the memory of Google Colab, but that's, Google Colab's issues. If you manage to run the complete inference, that basically the caption of the audio that it gives is a digital drum is playing a loop. So it depends on the model that we use, the size of the model. The inference result is different. And of course, it's way more, let's say, correct or closer to what actually the audio is, or what is happening in the audio. I have the audio here. So that is the description. And if we try the larger one, it's actually more precise, let's say. But it still describes something. This is the audio that we are inputting to the model. And just remember that the prompt is just captioned audio. Okay, so
maybe we can wait here, and if any of you have some problems with this, I can go through and help you. And just to mention, to highlight this audio music is generated by some LLM from internet. So I was trying to try here.
Yeah, basically the thing is that one of the things that we've talked about as well to work on during the workshop is to evaluate how correct or how this output of the open-ended question is in terms of evaluation, because it's not always correct or incorrect. There's no ground truth as such. If we say caption the audio, then what's the output, the ground truth? How we evaluate the correctness, let's say, of the output of the model, that's, of course, another issue. And as I said, depending on which model of Audio Flamingo you are using, then you can get some inference result or other one, and it might be still correct. It's just a different caption, or more precise, or that requires more reasoning, things like that. Okay, so everyone managed to run the inference? It's still running? Okay, yeah. It's yeah, I put your token here. So you have to change that. It takes, it doesn't take that long. The inference is just mainly loading the model. Then for the next examples, we load the model and then we can do inference on different ones. But this is the thing that sometimes runs out of memory and it's killed, and then the second time it usually does the thing. It ran for me at the first time, but it depends on the Google Colab requirements. Okay, so this is mainly up to here. What we've done is only to explore parts of the audio encoder, how it is basically representing text and audio, and how the model after that it's able to respond questions out of the audio. In this case, we had only a few audio files, and you can, of course, play with them. They are there in the assets directory. And since, well, we didn't want to infer over the whole data set, and this is the smaller model, we don't want to compare in terms of performance with respect to the whole data set. But one of the data sets that already also Ramani mentioned this morning is this setup, this MMAU, in which basically it's meant to challenge the model in terms of responding or answering questions that need reasoning in some way. So basically, this is what we were seeing this morning. So what we want to achieve is different tasks. So we want the model to have comprehensive skills in which we need to understand the world and then reason out of it to respond. Then the data set also covers different audio modalities, let's say, speech, music, and sound. So that's the three parts that is covering mainly, and depending on what's the data, the input data, then we have different tasks. So for example, one of the things that the data set comprises is speaker role mapping. So we have some examples here. Then tongue twisters, because that's something from which we need the model to be very specific to get information out of that. Then sociocultural and music understanding, scene understanding, so it has different skills. What is the model, the data set, or the benchmark data set comprising? So it has 10,000 audio clips, which are paired with human annotated natural language questions and answers. So we have the audio clips and question and answers, covering, as I said, the main domains in audio, which are, or three of the main domains, which are speech, sounds, and music, 27 tasks, which are either from reasoning or we need only information extraction. And then what we are going to use here is the test set, which is a reduced set out of the whole benchmark, which has 1,000 questions, and basically it still reflects the same distribution as the whole test set. Here are some examples of questions and answers that the model can do. So, sorry, the benchmark includes, and what we are going to test the audio flamingo on. So we have, for example, if we refer to sound, this is one of the domains that it covers. It could be, for example, if we are extracting information, we need echoacoustic knowledge. One of the questions that is prepared within the benchmark is, what natural environment is most likely represented by the audio? It's given, so in this, most of the questions, if not, I think all of them, in this case are multiple choice. Not all of them have the same number of answers or choices, but many of them have 4. We will see the stats in a while. So, for example, if we ask the model, what natural environment is most likely represented by the audio? And we give the model 4 choices. A serene forest, a quiet library, construction site, a peaceful beach. So the answer, we see here the image representing the audio. I don't have the audio. Is a construction site. What we can do as well in this domain, in the sound domain, we could do some reasoning. In this case, the subtask is temporal event reasoning. And the question, for one example of the questions is, for the given audio, identify which of the following sounds can be heard for the longest duration. Why is this event or temporal event reasoning? What do we need to reason to? I mean, what's the model needs to attend or pay attention to answer these questions? It needs to understand what is the sound for the longest duration. So that is a key thing in which we need to listen to the audio, understand that the longest duration is the one that it's covering most of the audio, and then answer. The options in this case were, well, video game sound, music, sound effect, and background noise. And we have the correct answer was a video game sound. Then this is the sound domain. What happens with speech? In this data set, we have, again, some questions that are information extraction and some questions that imply reasoning. So we have, for example, phonological sequence understanding, which is for the given tongue twister. So we are already giving some clues about the audio because it's given that it's a tongue twister. Identify which word appears first. Iron, aluminum, copper bottoming, or none of this. And the correct answer is B. But what about questions that imply reasoning? Well, for example, one of the tasks is a multi-speaker role mapping, in which we have multiple speakers in the audio, and we want to identify what are the roles of the speakers. The question in this case, in this example, is identify the role of the first and the second speaker in the conversation. Of course, it's not only given the roles, but it's also given the order of these speakers. And, well, the options in this case are parent, child, teacher and student, and doctor and patient, and coach and athlete. So it was doctor and patient. And then we have the third domain, which is music. Again, information extraction For example, regarding harmony and chord progressions, one question could be, which chord progression is used in the audio? And well, it's giving us the chords and the correct answer. And again, reasoning on music, we could ask for the emotional tone. And it's basically, what is the overall emotional atmosphere created by the combination of instruments in the audio? And well, we have different options. The correct one is unique and hard touching. So what is this setup? Basically, as Ramani already mentioned, humans have quite high performance in answering these questions. However, the model achieves much less, so it is challenging. So just to explore a little bit the reduced part of the dataset, the test mini part of these 1,000 examples, we have these pieces of code from the JSON file, and we can explore some examples. Here you have some questions. You can select them. You can even get the audios from the repository. I think it's, yeah, you can go to the repository and find the audio if you want to test any of them. Of course, you can play with the notebook as much as you want. And what we have is the questions, the choices, the correct answer, and then, well, what's the data set that comes from, the task, whether it's sound, speech, music. Well, the split is, all of these are test mini, and whether they are reasoning or information extraction. And then, apart from the main category, we have subcategories, and another tag, which is the difficulty of the questions. If you test the model on easy or difficult questions, of course, you will see that the smaller model of Audio Flamingo that we have here are, well, usually the easy ones are easier as well for the smaller model. Here you have the count of how many choices, answers, and so on we have. Either unique, because we have 1,000 questions, but only 800 unique ones in this set. And regarding the category, so reasoning or information extraction, well, this was a different tag, but it's mainly with this. So we have about double reasoning questions and information extraction. And here you have that it's, well, it's equally balanced in terms of domains, music, speech, and sound. The category, as I said, is 2/3 basically is reasoning, and then information extraction. And here you can see the different, these are the different data sets from which these audios are extracted from. So we have audio set, which is one of the largest one. Then some music, there's some synthetic data as well. And, well, some of the mockup or some music and some other data set. Speech is also from Voxelab, which is very well-known data set for speaker recognition. We have, as mentioned before, 27 categories or subcategories. Categories is reasoning or information extraction. And here you can see the distribution regarding subcategories. And, well, here we can see also how many, within the multiple choice, most of them have 4 options, but there are some examples in which we have 2, 5, or 8 different choices for the model to choose from. For example, if we look at some of the examples in which we have only 2 choices, we can see, for example, which word appears first, and it's just choosing between two. So here, of course, the 50% is the random. So you can explore as well, and you can, well, get some examples per subcategory. You can have some time afterwards to have a look at some of the questions and try to find whether the model is able to respond or not properly. You can, as I said, even listen to the audio. This is just the same data set, but just a different distribution of the, or configuration of the JSON file. And mainly what we wanted to see here from this file, but is, as I said, the same data set, is the length of the audio clips. So most of them are around 10 seconds, but we still have some longer ones and shorter ones. So we can also use it for different lengths and test it on them. No questions so far? Nothing? Okay. So this is up to here. Yeah? I think you need the microphone.
I was just, because I obtained with when I passed the audio that it has to classify the environment, it said exactly what you obtained. In the other test, I obtained different numbers than you, the distance, it was like different. But the text to classify the sound, the music, it was exactly the same. It is.
I think it's because the seed is fixed in the inference setup, but if you change the seed, probably you get something different. Because I checked with different, in the script that runs
each time it
is a fixed seed.
Each time if you put the same prompt, it will give you always the same. The optimal answer would be always the same text.
Yeah, the thing is that we configured the decoding of the text to be greedy decoding, so it's going to be always the same. You can change that thing, and after we have the possibility in the end of the notebook, if you set some different strategy for decoding, like for instance beam search, or it's just a matter of how you decode the information.
Yeah, but it's something that we have configured, but it's not giving you all the time the same answer if you don't fix the seed. It was just for testing purposes. Yep. The microphone.
It might be a bit late, but you mentioned in the reasoning task the duration, the longest duration. This is a little bit ambiguous, at least for me. Does it mean the longest consecutive duration or the longest duration, even if it's pieces?
You mean if the...
Yeah, you mentioned an example of what is the longest audio sound, right? So
yes.
The longest duration. And
yeah.
For duration, I was puzzled if it means if you have something like beep, 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 and it's very frequent, or you have something like woo.
Yeah, I understand. To be honest, I think that if you still have the same sound in different ways, I would still consider it the longest. So it's out of the, let's say, two sounds that you have, what is the one that you hear most of the time? So I wouldn't think it's restricted to consecutive, but it's a very interesting thing to test if the model is actually understanding consecutive or not. I'm not sure about that.
Okay, thank you.
Okay, so now, apart from running things, we want you to at least test with some of the questions that you might come up with, even if they are very simple or very difficult. It's up to you. Here, out of the audios, or you can even add some audios and load them and try to test the model there. We can basically have some of the, well, this is just breaking apart the loading the model here, and once the model is loaded, then you can basically do the decoding. Here you can ask any question out of the audio that you select, which is here. You can change the audio, of course. And then this will be your prompt. This is the audio, and then you will get what the model responds. For example, if we have the audio of the coughing, and we ask what is the gender of the person, the model basically responds that the person is a man. If we ask, is the person ill, the model says yes. It's because it's a minute of a person coughing, so it's pretty clear. So even if the model is very small, it gives you some surprising answers. There is another question that Sarah tried before. It was, where should the person of the audio go? And the model answered, go to the hospital, which is, of course, something that needs reasoning. Okay, this person is sick. It should go somewhere where it can be safe. So please run some examples and let us know any of the examples that you get out from this audio or any other, if you want some.
Yes, and answering your question, here in this decoding, if you set this do sample to true, then you can get different generations. That's the.
Okay, so some time to work on them, and then we can move to the question and answering part from the Zoom and so on. But please run and let us know your questions. Yeah, the microphone.
This is more of an interesting observation, I would say, than a question. But I ran the dog barking one, and my question was just cat, question mark. The answer was dog.
Dog.
But then I did, is this a cat? And the answer is yes.
Yeah, I mean, it is true that we've found, this is the smallest model, and it sometimes just gives you something that is probably similar because many people ask, this is a dog? And then it has a lot of common with the others. So I'm guessing that that's one of the issues. I haven't tried with the larger. The larger one, of course, has much less mistakes, but this smaller one, you will find a lot of questions probably that you're not able to answer with this smaller version.
Yeah, and this is also that we are trying to work on during the workshop, but also happens here if you condition like the model with some text, like imagine that you say something like, what is the zone in this domestic environment? Then the model, of course, there is some LLM there involved, is going to generate something, but that it's an hallucination because there is nothing domestic there. So we are trying to deal with these things during the workshop.
Yeah, because also, of course, the question, the prompt is giving some hints sometimes, and it's even making it confused some other times. So that's the thing. I don't find anything confusing in your question in this sense, but of course it's.
This is a general LLM problem, but when I also ask it, is this a dog? It says yes. But when I ask it, what is this person saying? It says, the person is saying, I'm a dog.
Okay, yeah. Yeah. It's, of course, you are basically conditioning on your prompt. So if you are giving some hints of the model, it's definitely doing that, yeah. Yeah, it's.
Oh, yeah,
Yep.
I was just going to say the same thing. I said with the coughing, is this person healthy? And it said yes. And then I said, is the person ill? And it said yes. So I think it does just tend to lean towards the positive answer.
Yeah, that's definitely. You can make it, it's a very small model, so you can make it confused quite a lot in that sense. And of course, we are happy to know the questions that the model is not able to answer, so we can work on it for the next 6 weeks. So you can have some time to run things and play with it, and we can set up the remote speaker to...
You saw this last part, which was this question-answer stuff. Now the next part is how do we make it better? And that is a big, big goal for this workshop. So we are trying to create at least 8,000 complex question-answer pairs. In this, and the goal is to have different kinds of music clips, sound clips. Most of them we will try to get from YouTube, and they have to be sort of new sounds which haven't been part of anything. And this is where we want as much help as possible. In one category which humans are good is music, and we don't have much music, good music in the data sets. So one goal is to sort of create a huge music data set. So a lot of us are downloading furiously and fighting YouTube. And by the way, if you have any expertise in how to download from YouTube lots of data, please share that with us. That is, it's a fighting battle all the time. You download a few and then YouTube stops you, and then you download a little more and YouTube stops you, and so on. And then we are going to use this data to create more complex data artificially by adding them together and so forth. So as one big thing which would be good, and we already got some feedback from some researchers at Tsinghua and from Katia here about music, because they have special expertise in music. People who are doing signal processing and learning often may not be so good at music. And the kind of questions we ask may not be that great. So people with domain expertise can this. Right now, we are trying to add all sorts of multicultural music. As we saw in Alicia's presentation, the audio that we had initially was between, at most, 90 seconds or something like that, not much longer. We're trying to get longer audio. We want to have questions which have multi-hop reasoning. So you ask a question, then you ask another question, and then you want the answer. You want to check chat. You want to check code switching, for example. So code switching is this habit when, if I talk to someone from India, I'll use a different accent because I'll use my more Indian accent. And when I talk to what my kids say that, you're talking like an American now. So, which, you switch unconsciously between one accent and the other, or one mode of speech and the other, and so on. There are many other options. Let's see. So there's a whole bunch of new skills. So for example, if I drop this on the thing, this is a plastic hitting wood. Maybe I can get that. On the other hand, if I dropped a metal, it might sound differently. So perhaps we can figure out things like collision, what's going on. If a long event is happening, a lot of animal sounds, action identification, textures, and so on. There's a lot of data in the song metadata, but you want to associate that with the sound itself. And a very interesting thing which was observed in video LLMs is if you presented the same query using text and using an image of the text, the model performed differently. And once you sort of train the model to also respond to the image of the text and to get the same kind of results, overall performance of the model improved. So this is called multi-format input. The same input is given in multiple formats. Perhaps this is something we can try for the audio itself. We will have a text version of the question, but we might use text-to-speech to associate with the input the audio part of the sound. Yeah. So for me, so again, there's lots of things we want to have: music with vocals, music without vocals. So we'll share this document with you. So this is almost like, extracurricular homework. Even if you're part of our team, of course, you should work on this. But even if you're not part of our team, we would appreciate you sort of giving us some spare time just because you're so interested in it. And for MIDI, there's some questions and so on. So we are working on this, and we've created a whole bunch of YouTube-based examples. So most of this work is being done by Vaibhavi. She's a student, master's student working in our lab at UMD. So let me show you this. So this person is preparing boba tea, and I guess the recording is binaural audio with ASMR kind of things. So they make all these weird sounds in it. And so now the training, as they make this stuff and they make the tea, you get all these sounds. And the associated question is, what is being prepared in the audio, and the answers are milk, tea, coffee, boba tea, milk. And the answer is boba, I guess. And so that would be the audio which would be fed in, and this is what the model would be trained on. And let's pause this. Let's see another question. So this is an audio with car sound troubles. Sound with a different sort of text label, and then you ask what was the. So this is an interesting audio because there is a sequence, so there is a numbering type of question, but also each sound is associated with a different trouble. So you can potentially ask questions like, what equipment has the fourth sound indicating trouble with, or something else like that. Anyway, so YouTube has, I don't know, I forgot the number now, 1 million pieces of audio and video uploaded every hour or something like that, or more. So you can imagine there is an incredible data set out there waiting to be made. And We just, yeah. Yeah, for this evaluation right now it's done manually. There is also thought of trying to do it using GPT-4o or so not GPT, Gemini, and we haven't yet figured that mechanism out completely, but we are in the process of doing that. And 5,000 is in one sense a lot, in other sense it's not that much. We can sort of, in one browsing session, you can easily go to 30 videos of YouTube, right? And I guess I'm not on TikTok, but people on TikTok go through many more than that. Yeah, so that is basically this part, and then we'll take the break now, and then Lasha will sort of conclude the thing. Yeah. Yeah.
Because this bubble tea...
Yeah, you can go now.
No? Okay. This bubble tea preparation, at least for me, it's like if I'm not watching the video and I close my eyes, then probably I'm not able to say that this is a bubble tea preparation. So, I don't know, the question, probably I need to help in this direction too during the workshop.
Yeah.
But...
and for many things, the answer is probably you cannot have enough information. But for many other things, actually, you and I may not be trained. But for the chef who's actually doing it, they can probably, or the person working in the kitchen, they probably already know what is going on. They have enough evidence from the sound. So it's a matter of training this system versus that person's system.
Okay, thank you.
Okay. So right now, we have like 100 questions, but we want to reach 8,000 actually, because we think we'll reject a bunch of questions after, but yeah. Okay. So now we are in the break, and then Lasha will take over.
So we will be using Lightning AI. I think everyone has access to it because training requires around 18 gigabytes of VRAM, and Colab only provides around 16, so just a little bit over the limit. So log into your Lightning AI accounts, then go to the main page and click on New Studio. Is everyone following? It's going to be very simple. So just click on New Studio here. Select your team space. And under the machine, we select GPU and L4. I think we don't have access to A10s and L40s, so let's just select L4. That's fine, and click on Confirm. Start. We will only be training on 5 samples, so it's very simple, and this model is not going to perform well. It's going to overfit, of course, but it's for demonstration purposes only. So there's a train.json file in the repository which describes sound files. Simply there's no notebook, there's just a repository which we will need to clone inside Lightning AI. Okay, next we'll clone the repo, code, copy. Just open the terminal, click on terminal and then new terminal. Then type git clone and paste the link. I'm just going to type it. .com. Okay, next we'll cd into the directory, cd AF2 into Audio Flamingo 2. And open this notebook, fine-tune.notebook. There are many libraries we need to install, so I'm going to use UV to do it faster. So pip install UV. And then we do UV pip install. This requirements.txt is one directory higher, so we need to do double dot. So as I said, there are 5 audio files only. You can take a listen to them if it loads. Doesn't work. Very simple files. And then we need to change this one path only. Simply do print working directory, pwd. Take this, copy, and then paste here. And that's it. We can run the code simply by clicking on Run All. Start. Since we only have 24 gigs of VRAM, we can only train a 0.5B model. We can specify other models here, so we can simply change to 1.5B or just 3B, but it's not going to work here. I've increased learning rate to 10 to the power of -4, which is 10 times higher than the usual learning rate. Otherwise, the model learns very slowly. And we have a batch size of 5 files. We are using all 5 audio files to train it, and 10 epochs. If the model is not already downloaded, it's going to download automatically, but it will be fast. It's actually the same model they were using for inference. And then the training will start automatically. We can see the current loss here. It starts at 5, and then it's going to start decreasing slowly. It's automatically saving all the checkpoints here, but unfortunately right now we cannot do inference. That's it. And we can also visualize how training loss progresses. If you keep it running, it actually goes to 0 because it's going to overfit since we are using only 5 samples. Yeah, I think that was it. Do you have any questions? Did you manage to run it? Just these samples. Yeah, these ones. So we have this sample, file name, question, and then answer here. Yeah, this is the one boom sound effect. I asked GPT to generate it for me. And there's another one, I don't know. I tried to use samples that were not probably used in the training.
Oh my God!
I think that's it. We can conclude here.
There are a couple of things we want to plan. Here we only use fine-tuning. We want to use preference optimization perhaps in the project as something to explore. We haven't, so this is just to show how to run a fine-tuning. So what Alicia showed was how to use the trained model. This is how to potentially train it to use.
We also wanted to demonstrate how the fine-tuned model would work, but unfortunately the code is not working for now.
And so this is with the AF2 model, which doesn't have speech. The AF3 module is almost ready to roll out. You can maybe give a quick summary about that.
Yeah, so the team from UMD is working on a new version of this model called AF3, which uses Whisper as an audio encoder, and it supports speech, music, and so on. And it can also support chat, so we can select an audio, load an audio file, then chat with it, ask different questions. It can actually write code, so it can also serve as a language model as well. Yeah, we have inference and fine-tuning scripts for it. So we will be working to add more data to it, such as Lion Disco 12 million and YouTube 8 million. And yes, that model performs much better and uses Qwen 2.57 billion model, which is twice bigger than the ones AF2 uses.